In assignment one, we're going to be working with the exFAT file system, but we're not actually going to be working with hard drives. It would be pretty cool for us to do that, but it's a little bit outside the scope of the course. So instead, you're going to be provided with some volumes that are exFAT formatted, but the volumes themselves they're binary files. And so that means that we're going to have to be doing things like opening and reading and working with binary files as opposed to working with a device like a hard drive. In class yesterday, in lecture 4, we spent some time building up an example that worked with a different binary format, which is called ELF. ELF is a format that is used for encoding things like program data. So when you're compiling your code with Clang, for example, it's producing an ELF file to put all the instructions and the data that you have for your program. I worked through this example in class yesterday, and what I'm going to do today is kind of just walk through this example from the main function, kind of going down as opposed to building it up from scratch again. So the very first thing I've got here is that we're working with, we're going to be working with files, and we're going to be working with some system calls. So open, read, and lseek. These are system calls that are used to work with files in general, but we're going to be working with them with binary files. Open returns something that's called a file descriptor. File descriptor is a numeric type. It's an integer, and it represents an identifier, a unique identifier for the file that you have opened in your program. You're going to be doing something similar to this in your own code, which is to have your own kind of file descriptor. But for the sake of working with binary files here, we have to have an integer that represents this thing that's called a file descriptor. I'm going to go down here to line 49, and this is the first place where we're trying to open the file. So the open system call takes 2 or 3 arguments. The first argument is going to be a string, which represents the thing that we're trying to open, and the second argument here is going to be some flags that we want to pass to this. So I want to open the second argument that was passed to me on the command line, and I want to open that read only. You can take a look at the manual page for open if you want to get an idea of what some of the other options are for open, but for now these are good enough. I don't want to make changes to the binary file that I'm opening, so I'm going to open it as read only. This line here is kind of what your mount function is going to look like, your NQP mount function. You're going to be passed a string that represents the name of the file that the volume, the exFAT formatted volume is contained in. And so you're going to have to open that file to be able to work with it. The very first part of an ELF file is a section that's called the file header. The file header is similar in concept to what we have with the main boot sector in exFAT. This is metadata about the file itself, about the ELF file. I am able to read the entirety of this structure in one go without having to read different bits and bytes from the file. I like to do it this way because it's a lot simpler. We can just do one read instead of doing many different reads. It's possible to read every one of these different properties one at a time from the file if you want, but that's kind of tedious to do that. And so I find it a lot easier to just read the whole thing all in one go. So to start, we declared this file header at the top. We called it fheader, and I've assigned it the special value of curly brace 0. That is a special notation that says I would like to initialize this file header. This is a stack allocated file header variable, and I'd like to initialize it with zeros. So all the values that are in the structure will be set to 0 when it's initially set up. I'm going to pass this to read. So I'm passing the address of this thing. Because this is stack allocated, I'm going to put this address operator here. And I want to read this many bytes. I want to read as many bytes as is necessary to fill up this structure. Once I've read that in, then I can start working with it. And so the very first 4 bytes of this file header, and this is the very first 4 bytes of the ELF file, is this thing called the magic number. This is a special set of bytes that tells us that yes, we are indeed actually working with an ELF file, and those are 0x7f and then the letters, the ASCII characters E, L, and F. So after we've confirmed that we have an actual ELF file, what I want to do then is I want to start printing out some information about the file header. And so I've created this function that's called print file header, and I'm passing the address of the file header. So just like I did with read to that function. I'm going to zoom way up here to where I've actually done it. The function that I've declared here is taking a pointer to a file header. And so that's why I'm passing the address in the main function. I'm doing some preconditions here, like I want to check to make sure that the header is not equal to null and that the ELF class is either a 32-bit value or a 64-bit value here. And then I have a conditional statement. So this is defensive programming, checking to see that the header is not null before I do dereference it. What I'm doing inside the conditional statement here is just printing out a single value, and the single value is just one of the values that we get from this from the union itself. So when I'm working with this, what I'm going to start doing is I want to ask questions about the data that's in the union. So the union that I have here is going to be used in two different ways. One of them is if it's a 32-bit file, and the other is if it's a 64-bit file. The way that we know whether it's a 32-bit or 64-bit file is by looking at this ELF class property. The ELF class property says it's either 1 for 32-bit or 2 for 64-bit. And we use this value to decide which of these parts of the union to work with here. This is very similar to the directory entry types that you have with the exFAT format structure that I've given to you. The very first byte in the directory entry structure is the entry type, and the entry type then is going to tell you which member of the union that it follows immediately you should use. So this is where you're going to be able to do things like determine whether or not the directory entry that you read is a file directory entry or a stream extension or a file name. So once we've got this data printed out, I'm going to zoom way back down to the main function here. Once we've got this data printed out, the next thing that I want to do is I want to be able to start going to different places in the file. The ELF format will let us, the ELF format is structured into several different sections. The file header is the very first part, and then the next couple of places that we want to go in an ELF file are the program header offset or the section header offset. So this is going to take us to another location in the file that has different structures that are called program headers and different structures that are called section headers. As I said in class, ELF is a means to an end here, so I'm not really too concerned with what these things actually are. All I really want to know is that I have to go to this offset in the file to be able to find this other kind of structure that's called a program header. So to do that, I need to ask the same kinds of questions as I did when I was printing out the file header. I need to ask questions about whether or not this is a 32-bit or 64-bit file, because I need to know which of these two structures I'm going to be using to get the program header offset from. I am using that ELF class flag, and I'm using the names of the parts of the union to be able to get to those different parts that I want. Once I've got a program offset, the thing that I'm using to move to the location of the offset is this function that's called lseek. I'm going to quit my elf.h editor here, and I'm going to say man to lseek. Lseek is a function that will let you go to different locations in a file based on an offset. It takes a few different parameters or a few different arguments. The first one is the file descriptor. So this is the file that you're working with. The second is the actual offset that you want to go to. And the third is this thing that's called whence. On Linux, whence is going to be one of three things: seek set, seek cur, or seek end. Seek set is an absolute offset. So I want to go to exactly this location in the file. Seek cur is a relative offset. I would like to go to wherever I am right now plus this many bytes, and seek end is relative to the end of the file. The program header offset is an absolute offset, and so I want to go directly to that location, so I'm going to use seek set. When you're working with lseek, it depends on where you're trying to go that will dictate whether you want to use seek set or seek cur. So for example, if you want to go to the beginning of the FAT, then you would probably use seek set. If you want to go to some place within the fat, maybe you go to the fat first with seek set, and then you use seek cur after that to get to the next location. Once we're at the once we're at the program header offset, then we can start reading these program header types, and that looks the same as what we were doing above up here with the file header types. So that should give you the tools that you need to be able to work with binary formatted files. So opening the file, reading the contents of a file, and seeking to different locations within the file.